All right, good morning. Welcome back to Pre-Calculus. We are going to be talking about polar coordinates today, okay, graphing them. The little cat is, she's being a little vocal today, but she's also being a little, I don't want to be touched. So if I can get her, I'll show her on screen, but here we go. All right. So, here we go. We're recording. Good. Okay. So what we're going to be working with here is how to graph on these things. And I probably haven't mentioned this particular content creator yet, but the organic chemistry tutor does a really good job of supplementing pretty much every textbook that has, like, from algebra up to differential equations. He's really something else. So I'm going to use the same method he uses to do this. But if you need more examples, he's a good person to learn how to graph polar coordinates from. So here we go. Plot 6 points satisfying the equation r equals 6. Well, we get r equals 6. Theta is kind of independent. Okay, we just need points that are r equals 6. I wonder if I could do this a little bit. Okay, so we're just going to take our pencil here, and what I'd recommend, like, well, start with r equals 6 here, and here, and here, and here. It's just the 4 quadrants. Okay, nope, that's not right. Let's erase that one. Okay. Nope, I went there. Let's get rid of this again. All right, and all we need to do is find 2 more spots when r is equal to 6 and plot those. Okay, I would have liked to have been like a little bit more symmetric about things, but there's an r equals 6 on the 45 degree, and there's an r equals 6 on the other 45 degree, or one of the other 45 degrees. And at that point, plot 6 points. Okay. We're good. And then just go ahead and graph what's going on. It's a circle, right? Because theta is independent. Why do they tell us to place the first point and the second point? They've already gone through and made us do all of that. But whatever. All right. Checking our answer. And so that's I'm not going to ask you this one on a quiz. It's way too easy. All right. But it's a good warm up. All right. So let's move on. Okay. We'll do this one too because it's a little weird. Okay. Plot points theta equals 3 pi over 4. Okay, graph the polar equation 3 pi over 4. So let's go ahead and graph some stuff. We have 3 pi over 4. Now, what if r is equal to 1? That'd be here. That's 2. That'd be here. If r equals 2 and theta is still 3 pi over 4, still 3 pi over 4, still 3 pi over 4. Okay, just it's in the negative direction, but it's still the angle is still 3 pi over 4. It's just that we're going in the opposite direction. This would be like negative, I guess, 6, 3 pi over 4. That's what would be happening here. So it's just a line, goes to the origin. Well, place the first point, place the second point. There we go, and then we're all set. They get harder, I promise. Okay. Skip that one. Skip this one. Well, maybe I don't promise they're going to get harder. All right. I'm going to do something about our graphing of polar coordinates that I can't do anything about it this semester, so I'm kind of stuck. All right. I will probably release a little bit of an addendum to this section here. All right. What other kinds of things am I going to ask you to do? Because that was a pretty underwhelming experience with graphing polar coordinates. Okay. So there's effectively three types of polar, well, there's one type of polar coordinate that I'm going to ask you. Okay, and that is r is equal to a plus or minus b sine theta, or a r equals plus or minus b cosine theta. All right, those are the most common ones you come across. All right, so let's go ahead and take a look at how do we do this. All right, so we'll do case one. Okay, we'll say, how about 3 plus 3 sine theta? Okay, when a and b happen to be the same. So our first case is a is equal to b. All right. So what are we going to see here? What I would like you to do is to graph this. So our step one, actually let's do this. This will be step one. Okay, graph on an r theta Cartesian coordinate system. Okay, so what we're going to do is we have 3 plus or minus 3 sine theta. Okay, so I know the worst case for sine happens to be -1, right? The lowest case for sine is -1. That would be 3 minus 3, which would be 0. So this is strictly above the axis here. Well, it could be on. So I'm not going to have anything in quadrants 2, or quadrants 2, 3, or 4. We're just going to be dealing with quadrant 1. We're just going to graph one cycle, one period of sine. Okay, this is pi. This is pi over 2, and this is 3 pi over 2. Now, even though this is my x equals 0, or r equals 0 in this case, okay, what I'd recommend is we're going to draw in like a little dotted line here of my actual axis that I'm looking at, okay, because going back to college algebra, this 3 is a vertical shift, right? This 3, this is a vertical shift. So all we're going to do is we're going to take this 3 sine theta and we're just going to move it up three points, three levels. So really, I'm going to think about this brown line here as my axis, okay, because I know that's where all that's everything is relative to this 3, okay. So let's go ahead and okay, so that's my 3. This is 4, 5, 6, 2, 1, none. Okay, and how do we graph 3 sine theta? We said, well, the first point, right, when x equals, when theta is equal to 0, r is equal to 3, because theta is equal to 0. So sine 0, or sine of theta 0 is 0, so we just have 3. When we get to pi over 2, right, sine gets up to 1, right? Sine grows to 1. So we have 3 plus 3. We are up here at 6. All right. And when we get to pi, right, sine of pi, that's back to 0. So we have 3 plus that. So we're down here again. 3 pi over 2, right? Theta equals 3 pi over 2. Then we have 3 minus 3. That goes down to a 0. Okay, and then back to 2 pi, this turns back into a 0. We get 3 plus 0, back to 3. Okay, so we're going to sketch this part in. So you didn't think you were ever going to have to graph trig functions again. Okay, but here we are. All right. So let's go ahead and graph this on polar coordinates now. All right. So again, we've got our coordinate system. We've got the coordinate system, except now it's not x and y. It's 0, pi over 2, pi, 3 pi over 2. All right. It would be nice. I don't have one. I don't have a way of marking off specific denotations here. So we're kind of stuck. I'll try my best. All right. I usually, in a classroom, I usually use an eraser as a measure so I can do that. Okay, but I can't do that on a computer screen very well. Okay. I guess I could take my stopwatch and put it here to do that, but that's not really going to be that effective. Okay. So what we're going to do here is we're going to examine this graph and translate our Cartesian coordinate graph to our polar graph. So case in point. Okay. Use that gray. Okay. So when theta is equal to 0, right, this polar coordinate r is equal to 1, 2, 3. Here's my point. Okay, r is equal to 3. When we go up to pi over 2, we're going to be looking at 1, 2, 3, 4, 5, 6. Okay, so from at pi over 2, we're going to be up here. So what we're going to do is we're going to have r go from 3 up to 6. Right, so each of these values, right, is getting a little bit bigger here. It's getting a little bit longer, getting a little bit bigger, all the way up to 6. Okay, so that's our quadrant 1 occurrences. Quadrant 2, right, we are going to be going from pi over 2 to pi. What happens to our r? R goes from 6 down to 3. Okay, so we're going to have 1, 2, 3. So r is going from, see, this would be nicer to have a ruler or something. Let's call that 3. So r is going to go from 6 down to 3. So again, we're going to go from here. Okay, and the reason it's chosen here is because where's my theta? My theta is at pi. Okay, so now we're going to be in quadrant 3. We're going to go from pi to 3 pi over 2. We're looking at this region here. All right, so what's going to happen here is we go from 3 down to 0. Okay, so we go from 3 down to 0. So here's 3 and here's 0. Okay, but it doesn't just do so like in a straight line. It kind of decreases over the angle. So as I'm sweeping through the angle, right, the size of what's going on is getting smaller and smaller and smaller and smaller until it gets to 0. Now, from 3 pi over 2 up to 2 pi, so it goes from 0 back up to 3. That's going to meet back up here. Okay, but it doesn't just like do it in a straight line. It's circling around with the angles here. So what's going to happen, right? So we get a shape like this. Okay, this is called a cardioid. Okay. And there's an obvious reason as to why, right? So this is a favorite type of thing. If you used a cosine, then it would go on its side, right? If I change the order and put like a -3 here, then it would probably be upside right. Okay, so you can change like which orientation this is going to happen in, depending on if there's a plus or a minus in here, or if there's a sine or a cosine. Okay, but this is an excellent sort of starter problem. So if I would, if I was just starting polar coordinates and I was really unsure of myself, I might do 2 to 3 problems just on this, where the a and the b are the same. You can put a minus in here, you can put a minus there, and you can change the sine and cosine. Okay, so a equals b, okay, but you can change the plus or the minus. You change the plus or the minus in the middle. All right, you can change sine or cosine. Okay, but practice some of those. Okay, next. What if we set it so that we have a equals b? Why don't we set our phase 2 or our condition 2 where a is a bigger number than b? Okay, so we want something like 4 plus 2 cosine theta. Okay, something like that. Okay. maybe 3 and 1, 5 and 3, something. They don't have to be 2 apart, right? They can just be 4 and 3. That's fine. Okay, but this is the one I happen to choose. Okay, so step 1, right, is we're going to draw our r theta values. All right, technically this is my r is equal to 0, and we have to go up to, if cosine is 0, then it's 2. 2 plus 4 would be 6. We have to go 1, 2, 3, 4, 5, 6. All right, and we have to realize that we are dealing with a 4 as a vertical shift. So we're going to 1, 2, 3, 4. And effectively, this is going to be my, I'm going to think about this line here as my axis, even though it is r is equal to 4. Okay, so we're going to go back, say something like, actually, let's go ahead. Yeah, I use that. So let's go back and we'll call this, right? We'll call this pi over 2, or 2 pi rather. And halfway is going to be at pi. And then we have, it's not really a good half, but pi over 2, 3 pi over 2. And we're just going to draw in our 2 cosine theta here. So when theta is equal to 0, cosine is equal to 1. 4 plus 2 will be up here at 6. Okay, when pi over 2, 90 degrees, pi over 2, cosine is 0. So we have 4 plus 0 just there. We get to negative 1. Pi is cosine of pi is negative 1. So we effectively have 4 minus 2 because of that negative 1 there. So we're down here. Okay, 3 pi over 2, again, we're at 0. And then 2 pi back to 1. Cosine of 2 pi is 1. 4 plus 2 would be 6. Okay, so we're just going to dot in our cosine here. All right, pretend that looks like a cosine curve. I know it's a little weak. All right, so we're going to go down here. Okay, and what's my maximum? My maximum was 6. My minimum was 2. Okay, so we're going to need at least a 6 sort of a length here. Okay, we're going to have to go from positive 6. I know that the last one was 2, so I could probably get away with picking a slightly shorter value here. This is 0. This is pi over 2 for the angle, pi for the angle. Okay, 3 pi over 2, and then 2 pi. Okay, so where are the grids for the angles? Why aren't those in there? It's not just that, it's, but what we're doing, like if we wanted to do pi over 4, we would have a pi over 4 value. And we'd have a pi over 4 over here. It's just an, or 5 pi over 4, but this would be 5 pi over 4 in the positive direction, but negative r in the pi over 4, it would be in the negative direction if it went this way. So let's go ahead and graph this thing. Let's go ahead and change. I think I used ray like this. Okay, when theta is equal to 0, r is equal to 2. Okay, so let's go with 1, 2. All right. Oh no, so it was equal to 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. Let's erase this first part just in case. All right. So theta equals 0. Our function, our r value is 6. Now, as it sweeps up, right, as we sweep from here to pi over 2, what's happening? Well, the r is decreasing. It's decreasing back down to 4. Okay, so we'd have to go 1, 2, 3, 4. Right, so we're going to do something like this. We have 4. Okay, if you're old enough to, I used to do this in the 80s. I don't know if they have it in the 90s or not, but they used to have like laser shows. They would do it in a planetarium and show like laser light shows on the thing. And they'd have all these little shapes going on. They'd rotate them and move them in and out, things like that. And it's like That looks like polar coordinate system curves, because it was. And then my friends looked at me and they said, you can't come with us anymore. Okay, you have to not spoil our fun. Okay. So here we go. Pi. And I was friends with nerds, so I'll just tell you, that's pretty bad. Okay, and doing something like that. Okay, it's not going to be a heart. Okay, and from pi out to 3 pi over 2, we go back up to 4. Okay, it does have a little dimple in here. Okay, pi over 2, what was our value at pi over 2? It goes back up to 4, so let's go with 1, 2, 3, 4. Okay. So yeah, they listen to Pink Floyd and stuff while we're doing that. Probably tells you everything you need to know about what kind of a scene it was. Okay, something like that. But it's not a sharp point like it is in the cardioid. It's kind of a smooth little dimple in here. Okay, and then from 3 pi over 2 at the 2 pi again, we go from 4 up to 6 again. Okay, and I drew this horribly. It's called a limacon or limacon. Okay, it's that way. I don't know what this language where limacon comes from as far as which language it's from. We were just told like it kind of looks like a lima bean in a weird sort of a way. It kind of supposed to look like, you know, something like it's supposed to be rounder. I'm not doing justice to this in any way, shape, or form. Okay, but it's supposed to have like kind of a dimple in here, and we're doing this. Okay, so that's again that's what these look like. I'm not gonna get on you too much if there's like a dimple or not a dimple, but you could do that. Actually, hold on for 1 second. I'm gonna pause you for a moment. Okay, back to our old friend Desmos here. We'll go to our graphing calculator. Now you have to use R and theta with this. You can't use it any other symbols. They insist on R and theta. But instead of a grid, we're going to go ahead and we're going to do that. So it will, you know, it'll understand that we would like polar coordinates, please. Okay, I'm going to go one more thing over to the wrench here. So with the wrench, you hit the grid. I'm going to go ahead and make it bold. Okay, but then we're good. So if I wanted to type this in, right, we have R equals 4 plus 2 cosine. Now this is what you have to do. Okay, theta. Otherwise, it won't do it. Okay, I'll go back to a coordinate system, not like it. Okay, but that's what it's supposed to look like. Okay, I think if we make these guys closer together, we'll see a little bit more. See, now you can see like the little dimple there. If we do a 3.5. Okay, so the closer that this gets, the more pointed this is going to get. Okay, but there's a nice little average you can have there. Okay, 2.5, 2.5. All right, but you know, kind of an exaggerated lima bean thing. Okay, so that's what we have. Okay, the cardioid. What was it? 3 plus 3 sine theta. Okay. Oh, we need R equals, otherwise it won't like that at all. R equals. You can see it's a little bit rounder because you know, it's better at drawing things than I am, but that's what it's supposed to look like. Right. And later when you get to Calc 2, like they're going to ask you like, what's the area in this lobe here? Okay. Or what's the area in half of this thing? Or what's the area? How much arc length? How long around is this? Like what's the arc? It's not 2 pi r, right? It's not the circumference of a circle. But in Calc 2, you're going to learn how to do arc length, and they might want to know like, what's just the arc length between this point and this point? So you just go all the way around. Okay. So you say, well, why can't I use this for a calculator? Like you can, but if you got to get out the calculator and work on this thing, like maybe there's going to be a circle r equals 3 cosine theta. And it might ask you like, hey, what's the area in here? So you're going to have to know like where these guys intersect, where they intersect. Okay, or like what's this moon type shape here? They might want to know that. And like I said, you can use calculator for this. It's fine. But if it's going to take you any amount of time to do calculator on this thing, because you got to remember all of this. You got to remember it by hand too, I guess. But this is only going to be like this setup of your Calc 2 problem. This is not like the whole thing. So being able to graph these things today, tomorrow, you don't have to go so fast. Eventually, you'll get faster. Okay, but you might have to graph one of these things by hand and then shade in the part that you want the area of, and then go ahead and set up your Calc 2 problem in order to get that. Okay, but that's where this is headed. So you know like where it's going to go. That's why we kind of want you to be able to do this quickly, or at least by hand, like just sketch it out. We're not looking for an exact picture here, but we have to do something in order to sketch out our problem. Okay, what about, this is the hardest one. Okay, what if B is greater than A? Okay, so why don't we do something like 3 plus 2 sine theta. Okay, we did a cosine for the second one, we did a sine for the first and the third one. Okay, but effectively you want to do that. You want to say A plus or minus B sine theta or cosine theta, and pick your A and your B depending on what you want. Okay, and then try to graph it, test it into Desmos to see if it's getting the right answer, and then you can practice. Sorry, I had to sneeze. Okay, why don't we look at this one? All right, so what we're going to do, right, step one is graph it in the Cartesian coordinates. Step two, this has an additional step two. We're going to find the zeros. Okay, and step three is graph on polar. Okay, step two in each of the cases above, we didn't actually have because it didn't cross the axis anywhere. So we didn't have to worry about like where do we have to go backwards. Same thing here. With no axis crossing, it touched it, but it didn't cross it. So there was no backwards sort of things to deal with. All right. So we have 0. We have 2 pi. Erase this so I have a little bit more room here. All right. So we're going to draw this. Here's pi. Actually, I need to insert a whole bunch of room here. All right. One, 2, 3, 4, 5. 1, 2. We're going to go from 2 pi. Here's pi. Here's pi over 2. Here is 3 pi over 2. Now let's go ahead and sketch this in. 3 plus 2 pi. This 3 again is a vertical shift, so I'm going to go ahead and dot in the axis I'm thinking about rather than the actual axis. All right, and then we're just going to draw our values here. This is not what I wanted. I wanted B greater than A. 2 is not bigger than 3. There, that works better. Right? So again, here's my axis. Okay, now that we have the problem written down correctly. So my idea here with sine, right, is I've got to deal with 3 sine theta plus 2. Okay, that's my R. So at 0, right, sine of 0 is 0. So we're just here at 2. Okay, we'll go here at pi and at 2 pi. Sine is 0 in all those cases. Now pi over 2, sine is 1. So we have 2 plus 3. We're going to be up here at 3. Okay. Now at 3 pi over 2, we're here at negative 1. So that'd be 2 minus 3. That would be down here at negative 1. Okay. So let's go ahead and graph our sine. Okay. Now, here is a question. Where does it cross? Okay, where does this thing cross? And the way you do that, that was my function, 2 plus 3 theta, 2 plus 3 sine theta. Where does it cross? That is equal to 0. Okay, so we have to solve this. So we're going to say sine theta is equal to negative 2. Sine theta equals negative 2 over 3. Where is that? And again, it doesn't matter if you work in degrees or in radians. Again, for the sake of simplicity, we're going to go ahead and say theta is equal to sine inverse of negative 2 over 3. All right. So we're going to say we have inverse sine, or arc sine, depending, of negative 2 over 3. And this is going to be in degrees. Okay, so it's very careful to remember that. So this is going to be negative 42-ish. I don't know where negative 42 degrees are. How do I turn that into something that's in the first, or how do I turn this into a positive angle? Right, we're going to add 360 to it. Okay, and that's going to be 318 degrees. Okay. So here is one of them. Okay, this is negative 42 degrees or 318 degrees. There's another one though. There's another angle that's negative for sine. That's in the third quadrant. Okay. So since this is 42 degrees under the horizontal, this would also be 42 degrees under the horizontal. So this is 180 degrees. This is an additional plus 42 degrees. So this angle here, right, this whole thing all the way over, this angle is going to be 180 plus 42. 180 plus, this is 41.81. 41 plus, oh no, 41.81 is equal to, we get 221 degrees. It's effectively 222. Okay. The reason why I'm so cavalier about rounding like this is my graphs suck. There is no way I'm going to see 2 degrees on this thing. Okay, let alone 0.1 degree. Okay, it's just not going to happen. But that's approximately where, okay, where we're going to be doing this. We can convert to polar. Okay, so what's converting to polar was 221 divided by 180 times pi. So this is 1.23 pi. Okay, 1.2 pi, and then 318. Okay, so 318 divided by 180. Okay, so this is about 1.8 pi's. Right. So if I'm going to be looking at here, right, this is 1.2 pi. This is 1.8 pi. Okay, just so we have an idea. So now when I go to graph my stuff, right, how much do we have to go up to? We have to go up to 2, 3, 4, 5. We're going to go up to 1, 2, 3, 4, 5. Zero, pi over 2, pi, 3 pi over 2. Okay. So at x equals 0, or theta equals 0, okay, my r is equal to 2. Now, when I sweep up to pi over 2, we're going to be at 1, 2, 3, 4, 5. Okay, so we're going to 1, 2, 3, 4, 5. Right? Right? And that works out. Then between pi over 2 and pi, okay, it comes back down to 2. All right. Now, when it sweeps up from between pi and 1.2 pi's, right, sweeps between pi, we'll call this 1.2 pi as an angle, okay? It's going to come in and hit the axis, okay? R should be 0 here, all right? Now, everything else that happens here needs to go backwards. So at 3 pi over 2, we are at negative 1. So at 3 pi over 2, that would be 1, negative 1, okay? So what's going to happen is this is going to come in, and then everything you thought was going on over here is actually going on over here. So it's going to loop the loop in here, okay? And the same thing is going to happen on the other side. This angle right here, this was 1.8 pi. So that's where it goes back to being a positive value. Okay, so we are on our Cartesian coordinate system, we are here. And then from 0 up to 2 pi, it's going to grow back up to 2. But this is all in the fourth quadrant. Positive fourth quadrant actually is this way. So we're going to end up being out here. Okay, so it's got this little tongue in there or something like that, or the thing at the end of your tongue, end of your throat, so like, a little uvula here, or just a little loop-de-loop. However you want to call it, that's fine. Okay, I don't have a preference. I'm sure it has a name, but I don't know what it is. All right, so if I wanted to go ahead and graph this thing again, right, we'd say R was equal R. Come on, really? We have R is equal to, what was it? It was 2 plus 3 sine theta. Let me turn these other ones off so we can have actually a clear look at it. Okay, you can see it's got this little loop-de-loop thing in the middle here, but again, it's a little bit better than mine is because it's not, mine is not quite as round as theirs is. Theirs is a better picture. But again, we're not looking for perfection in graphing this. We're looking for a sketch. So I don't want you to look at that and say, wow, what's going on here? Okay, but I encourage you to play with this a little bit. You could say R is equal to a theta, and then add a slider for A. Okay, and we'll go from 0 to 5. Okay, you can mesmerize people here. No, keep that. So we can just kind of do this. Okay, and then go ahead and take a look at that. Okay, so that would be a spiral. It's not a specific spiral. It's not golden ratio or anything like that. It's just a spiral. Okay, but you could do that. A little bit easy, but that's okay. Let's see. I'll stop this so we don't get dizzy. Okay, we could do. There's one. We could do. Let's change this to 1. Okay, and we could do ln A. Oops, not there. We'll just, that's fine. Let's just go. All right. There's your asymptote right here. Okay. Notice this, it doesn't really do very much. Okay, it just doesn't. Because logarithms flatten everything out. Okay. But we have that. So amaze your friends. We do have one that I should pick out to you. This one's kind of a neat one, but again, this is where my friend said, you can't come with us to these shoes anymore. You are killing our buzz. Sine of 3 theta. Okay, let's make this big. Do a 4. Okay, so you could do like a little bit of a, you do a rose. That's called as a rose. You can do 4. Okay, but now it doubles. 5. Odd numbers are nice because you don't have to go through them once. Okay, even numbers are a pain in the neck. Okay, but it works for that. Works for cosine too. It just changes what's going on. Okay. I don't know how to make it spin. But again, you might be designing something and you've got a fan or something and they just want to know, like maybe we've got to plate something on the edges of the fan. How much plating do we need? What's the length of all of these little loopy loops and all the pedals? Okay, you might have to know that. So this is one. This is on the crest. This is on the. I really don't want it, like, especially if it's 5. With 3, I don't feel so bad. Okay, but with more than 3, I might say to myself, calculators exist. Okay, we can graph this in a calculator and be a little bit easier about what's going on. Okay, so even in Calc 3, this is kind of like the hardest one that we would have to deal with. Okay, so I am very partial to asking you a question. A plus or minus B sine theta, A plus or minus B cosine theta. All right, so practice these formats. They are listed in this is also a Lemicon. Okay, there's more, but they are more complicated. Okay, there's one that looks like r squared is equal to sine squared. Okay, show you that. It's another propeller type looking thing. Okay, so we have r squared is equal to sine squared theta. Oh, come on, up there. Theta. Right. Now, wow, even okay, I'll delete some of my thetas, my r's. No, I didn't like it at all. Okay, well, that's in your book. I know I'm not a big fan of this particular one because it's hard to graph it by computer. It's hard to graph it. So good luck to anybody dealing with by hand, but it's possible. Okay, so I wanted to get through those because I am partial to the ones I showed you. Okay, that way when you go to a laser show, listening to Pink Floyd, you could also say, hey, those are polar coordinates. And then maybe your friends will tell you, you can't hang out with us. You can't sit at our table anymore. You're done. Please don't come to these shows with us. Okay, so that is the thing. You probably don't have laser shows anymore. This is not a thing you have to worry about. Okay, but that is how to graph in polar coordinates. So you could please play around with the homework and do those. They're excellent as a warm-up. But I urge you to try some of these. Check yourself against the Desmos and see. But please try to practice some of these too. All right, I'm going to stop and I'll let you go with that.